Welcome to the deep dive. Today, we're zeroing in on a really critical bit of kit inside those giant LNG carriers you see. Liquefied natural gas ships.
Yeah, it's fascinating stuff. We're talking about machinery operating under some pretty extreme physics. High stakes, really.
Oh, they are. Think about it. Shipping gas that's been chilled to minus 160 degrees Celsius. I mean, that's colder than Mars, apparently.
It's incredibly cold.
Yeah.
And even with the best insulation imaginable, some heat always gets in. It just does.
And that tiny bit of heat causes the liquid cargo to, well, gently boil off constantly. It creates this stuff called boil-off gas, BOG.
And that BOG, it sounds harmless, but it builds up pressure inside these massive cargo tanks. Fast.
Which is the core problem, right? Too much pressure and, well, you're risking the structural integrity of the tank itself, a massive safety issue.
Absolutely. Failure is just not an option there. So you need something constantly managing that pressure.
Enter the hero of today's deep dive, the low-pressure BOG compressor, the LD compressor. Its job is basically to keep everything safe.
That's its primary role, yeah. But it's doing so much more. Our mission today, really, is to unpack how this one machine tackles safety, meets really strict environmental rules. MARPOL and IGC is the big one here for air pollution.
Okay.
And at the same time, it turns what could be a hazardous waste gas into, well, useful energy. It's pretty clever.
The challenge, though, it starts right at the beginning, doesn't it? The pressure it's pulling this gas at is incredibly low.
Ridiculously low. It's sucking gas from the tanks at something like 0.05 to 0.25 bar gauge. That's barely above atmospheric pressure.
So the gas is almost useless at that point.
Pretty much. It's got no energy, no driving force. The compressor has to grab that and then boost its pressure massively, sometimes by 50 times, sometimes even 100 times, depending on what the ship needs to do with it.
That range is huge.
Yeah.
So let's break down the sort of threefold duty it has. First, the constant running is for safety, keeping the tank pressure okay, meeting the IGC code requirements for gas carriers.
Exactly. Avoiding venting gas to the atmosphere, which is bad environmentally, or flaring it wastefully. Job one is always safety and compliance.
Okay, so safety first. But where does the gas actually go once the compressor grabs it?
Well, the number one priority, economically speaking, is to use it, to fuel the ship itself.
So the ship runs on its own cargo boil-off. That's smart energy saving.
It really is. Most modern LNG carriers have engines that can run on this gas dual fuel, sometimes tri-fuel engines. But to make the gas usable for them, the LB compressor needs to push the pressure up.
What kind of level?
Into the 4 to 6 bar gauge range.
Right.
That's the sweet spot for feeding most ship engines. So you're turning this low-pressure waste into primary fuel.
But what if the ship's going slow or maybe idling? The engines won't need all that gas. Surely, does the cargo just get wasted then?
Good question. That's the constant balancing act. BOG is always being produced, right? If the engines can't take it all, the system needs a plan B. Reliquefaction. Sending the excess gas to an onboard plant that cools it back down and turns it back into liquid LNG.
Putting it back in the tank, basically. Preserving the cargo. That sounds like a big win, both financially and environmentally.
It's a huge win. You get the valuable cargo and you minimize emissions, helping meet those strict MARPOL rules we mentioned. But
There's always a but.
it needs more grunt from the compressor. To feed a reliquefaction plant, the LD compressor has to boost the pressure even higher. We're talking typically 6 to 12 bar gauge now.
Wow. Okay, so that's maybe double or triple the pressure needed just for the engines. This machine needs to be seriously flexible.
It does. And there's one more stop, the final safety net. What happens if the engines don't want the gas and the reliquefaction plant is maybe offline for maintenance or just can't keep up?
You still have rising pressure in the tanks.
Exactly. The absolute last resort is controlled disposal.
The gas combustion unit. The GCU, like a specialized high-efficiency incinerator.
Correct. It burns the gas off safely and cleanly. But even the GCU needs decent pressure to work properly to ensure complete combustion.
So the compressor has to deliver even higher pressure for that.
Yep. For the GCU, you might need to push the BOG up to, say, 10 bar, sometimes even as high as 16 bar gauge.
Good grief. So 4 bar for fuel, maybe 12 bar for reliquefaction, up to 16 bar for the GCU. This single LD compressor is the gateway, constantly adjusting based on where that gas needs to go. That sounds like a massive engineering headache.
It's a critical piece of engineering, absolutely. It enables the whole operation, juggling these different demands constantly.
Okay, so handling that pressure range is one thing, but it's also dealing with gas that starts off incredibly cold. Let's talk about the physical challenges there. What's the biggest danger when handling gas at minus 160 C?
The absolute nightmare scenario is liquid carryover, sometimes called liquid slugging.
Meaning actual droplets of that super cold liquid LNG getting sucked into the compressor, not just gas.
Exactly. Even tiny droplets. If that liquid hits the warmer, fast-moving metal parts inside the compressor, well, it's bad.
How bad?
You get something called liquid hammering. It's a physical shock wave and catastrophic thermal shock. Imagine hitting warm metal with something at minus 160 C. It can cause loud bangs, immediate severe internal damage, wreck the machine instantly.
Okay, so you absolutely cannot let liquid into the compressor. How do you stop it?
You need a guard at the door. That's the job of the BOG mist separator. It sits just before the compressor inlet.
A mist separator. Okay.
Its only job is to knock out any tiny liquid droplets, that mist, ensuring only pure dry gas actually enters the compressor. It's a non-negotiable safety barrier.
Got it. So assuming you've got dry but still very cold gas going in and you compress it, what's the next challenge? You mentioned heating.
Yes. After compression, the gas is obviously warmer than minus 160, but it's still often very cold. Before it can be used, especially by the engines, it needs to be heated up significantly, usually up to around positive 20 degrees Celsius. So basically, ambient temperature. Think about that swing from colder than Mars to room temperature.
That's enormous. Why is that heating step so crucial? Why not just send the cold pressurized gas to the engines?
Two main reasons. First, sending very cold gas down pipes risks forming ice, or worse, solid blocks called hydrates inside the fuel lines or equipment. That could block the fuel supply completely.
Right. Plugs up the system. Makes sense.
And second, engines are designed for fuel at a relatively stable, warm temperature. Feeding them gas that's still cryogenic or fluctuating wildly in temperature would cause huge thermal stress on the engine parts themselves. It would make stable combustion very difficult, if not impossible.
So the heating ensures smooth running and prevents damage downstream.
Okay,
Okay.
let's switch gears to the actual hardware. Given this really unique job, super low suction pressure, cryogenic temperatures, need for purity, what kind of compressors do engineers actually choose? Yeah, the selection is critical. One very common type, especially when gas purity is absolutely paramount, is the oil-free reciprocating compressor. You often hear them called labyrinth or Labai compressors.
Labyrinth. Like a maze. Are these the ones where parts don't actually touch?
Exactly. They use incredibly precise seals around the piston that create a complex maze-like path for the gas to get past. But the piston itself doesn't use traditional lubricated rings that touch the cylinder wall.
So no lubricating oil can get into the gas stream.
Precisely. That guarantees the purity needed for sensitive downstream stuff, like the engines or the reliquefaction plant, which can be fouled by oil.
Clever design. What's the main alternative?
Dry screw compressors are also very popular. These are rotary machines.
What are their advantages?
They tend to be more compact, which is a big plus in a packed engine room. And crucially, they generally offer very good turn-down capability.
Turn down. Meaning they can operate efficiently even when the amount of gas coming in changes a lot.
Exactly. BOG generation isn't constant. It fluctuates with weather, sea state, tank levels. A screw compressor can often handle those wide flow variations quite efficiently. That flexibility is key.
Okay, Lebi or a screw for the main LD duty. What about centrifugal compressors? They're common in other gas applications.
They are, but generally not suitable for this initial low-pressure stage. Not on their own, anyway.
Why not? They can move a lot of gas.
They're dynamic compressors, and they are very vulnerable to a phenomenon called surge at these very low inlet pressures.
Surge. Sounds bad. What is it?
It's basically aerodynamic instability. If the flow rate drops too low for the compressor's design, the flow inside can become unstable, stall, and even momentarily reverse direction, slamming back towards the inlet. Violently.
Ouch. That sounds like it would break things.
Oh, absolutely. Surge causes huge vibrations, massive stress, potential for catastrophic damage. The operating range where they're stable is just too narrow when you're starting near vacuum. They can be used, but usually as a second stage, a booster, after a Labai or screw, has already raised the pressure significantly and stabilized the flow.
That makes sense. First stage needs reliability at low pressure. Second stage can add the big boost. So managing all this, the varying BOG rates, the different destinations, avoiding surge must rely heavily on controls.
The control system is absolutely the brain. And the heart of modern control here is usually the variable speed drive, or VSD.
Right, controlling the compressor motor speed directly.
Exactly. Instead of running the motor flat out and using valves to control flow, the VSD lets you adjust the compressor speed continuously. You can precisely match its output to the actual amount of BOG being generated and exactly what the engines or the reliquefaction plant are demanding at that moment.
Which must save a lot of energy compared to just throttling a valve.
Huge energy savings. It's much more efficient. But the VSD also works hand in glove with the anti-surge controls we just talked about.
How so?
Well, the control system constantly monitors where the compressor is operating relative to its surge line. If the flow starts to drop dangerously low, maybe because engine demand suddenly plummeted, the anti-surge logic kicks in instantly. It opens a recycle valve that loops some of the compressed gas from the discharge side back around to the suction side.
Creating an artificial flow to keep the machine stable, even if the real flow demand has dropped off.
Precisely. It tricks the compressor into thinking it still has enough flow, keeping it safely away from that dangerous surge point.
Let's picture a tricky situation. Say the ship is maneuvering near a port, engines suddenly cut power, demand for BOG crashes. Pressure in the tanks starts to shoot up.
That's where the GCU control system becomes absolutely vital. It acts as that essential safety buffer.
The gas combustion unit controller.
Yes. In that scenario, the LD compressor, guided by its controls, can instantly divert all that excess BOG flow at that high pressure, the 10-16 bar range, straight to the GCU.
For safe, controlled burning.
Exactly. It ensures that even during really rapid changes, transients, engineers call them, the tank pressure stays safely under control. It's critical for operational safety during high-stakes moments.
And beyond just operational stability, there are layers of mandated safety systems, right? And under the IGC code.
Oh, multiple layers. You've got gas detectors everywhere sniffing for leaks. You have emergency shutdown valves, ESDs, designed to slam shut and isolate sections if something goes wrong.
And automated trips.
Absolutely critical. The control system isn't just watching flow and pressure, it's constantly monitoring things like bearing temperatures, vibrations, motor current. If any of those go outside safe preset limits.
The system shuts the compressor down automatically. No human needed.
Instantly. No delay. The automated protective trips have to be faster and more reliable than human reaction could ever be. Safety is paramount.
Let's talk sustainability for a moment. There's a trend now to retrofit older LNG carriers, isn't there? Adding reliquefaction plants where they didn't have them before.
Yes, that's a big move. Many older ships might have relied more heavily on just using the gas and engines or burning the excess in the GCU. To meet modern environmental standards and preserve cargo value, owners are investing in adding reliquefaction capabilities.
Does that mean ripping out the old LD compressor?
Often, no. That's the interesting part. The existing LD compressor might be perfectly capable mechanically. The main job is often upgrading or retuning its control system.
Reprogramming the VSD and the controls to reliably deliver that slightly higher pressure needed for the new reliquefaction unit, that 612 bar range we talked about.
Exactly. It allows them to extend the life of that expensive compressor hardware while significantly improving the ship's environmental footprint and efficiency. It's a smart way to upgrade.
And looking ahead, where's the intelligence in these systems going? Is it just about reacting faster?
It's moving beyond just reacting. We're seeing more digitalization, more smart controls that try to anticipate changes.
How does that work?
Well, the systems can integrate data from the VSD, from vibration sensors, maybe lube oil analysis, but also things like the ship's voyage plan. It might know the ship is scheduled to slow down significantly in, say, 6 hours.
So instead of waiting for the engine demand to drop and BOG pressure to rise, then reacting,
the system could proactively start to adjust the compressor speed or plan the BOG routing slightly ahead of time. It leads to smoother operation, potentially even better energy efficiency.
And predictive maintenance too, I guess, using sensor data to spot problems before they happen.
Definitely. Analyzing vibration trends, temperatures, motor performance. The system can flag up a potential issue, maybe a bearing starting to wear, long before it causes a failure. Allows for planned maintenance instead of costly breakdowns at sea.
When you really take a step back, this LD compressor is kind of the unsung hero of the whole LNG supply chain, isn't it?
I really think so. It operates right at this crazy intersection of extreme physics, managing gas colder than Mars, boosting pressures by maybe 100-fold.
While also being the key to meeting strict environmental regulations like MARPOL, following the IGC Safety Code, and basically making the whole business of shipping LNG economically viable.
It transforms that unavoidable boil-off from a potential hazard and waste product into either valuable fuel for the ship or cargo that can be saved and delivered. Its reliable, efficient operation is fundamental.
The efficiency of this one machine directly impacts the sustainability and profitability of global LNG transport.
Without a doubt.
Which leaves us with a final thought for you, our listener, to consider. We're already using smart VSDs, predictive analytics, integrated control systems to optimize these incredibly complex floating energy systems. Given that, how much more efficiency can we realistically squeeze out with newer tools like, say, AI? Are there still big gains to be made, or are we starting to run up against the basic laws of physics and thermodynamics governing how that LNG boils off and how gas is compressed in the first place?